Okay, so let's get started. There will probably be people entering. We had over 100 people registered for this webinar. So that's good news. We have over 50 people in the room now. So welcome to this Big Picture webinar. Today's topic is metadata. As a project, we've invested a lot of efforts into establishing a common metadata standard for the Big Picture repository, which is, we think, of key importance for a project like this. Today's speakers will be Maximilian Köhler from the Medical University of Vienna and Erik Gabrielsson from Sectra, who both led this endeavor, of course, with the input and from many project partners from both industry, academia, and SME. So we will have roughly 45 minutes presentation, so we have some time for questions afterwards. If they're burning more technical questions, I would propose to put them in the chat so we can also follow up with them while the speaker is still presenting. And I think that is it. I believe, Max, you will start. So please go ahead.
Thank you very much. Just a quick assurance, can everyone see my screen?
Yep.
Wonderful. So thank you very much. Good afternoon. I'm very grateful that I have been given the opportunity together with my colleague Erik Gabrielsson to present the first version of the Big Picture metadata standard, which is the output of the task force metadata integration here at Big Picture. And I want to start to give a quick outline of this talk today with a motivation. Then we will dive into the metadata standard and its substandards. And at the end, we will talk about metadata tools that have been developed in order to create datasets that comply to this standard. So the motivation for a standard stems from the need that we have defined that we will interact with the repository by the means of datasets. So datasets will be submitted to the repository, and once stored on the repository can also be downloaded. And we have decided that on the one hand side, the dataset structure that is used to submit data will be the exact same structure that is downloaded. And therefore, we wanted to develop a model that assures that we have a structured data exchange, but beyond that, also to harmonize the metadata that is contained within the dataset and also have a consistent interaction with data and metadata, for instance, with AI models or other toolings. Nevertheless, besides that, we also wanted to respect that we will have people that create those datasets manually and other partners that will automatically extract the data from LIMS systems, so laboratory information systems or clinical information systems, either fully automated or semi-automatically. And therefore, we wanted to have a structure that facilitates that both manual as well as automated data extraction is possible. But not only this, we also respected the heterogeneity of the subspecialties in the pathological domain, most notably between clinical and non-clinical. And we wanted to provide a structure that is flexible enough in order to encode and store metadata for all these different subspecialties, but at the same time being a structure that can be interacted with efficiently. And lastly, we also set the aim that we want to provide metadata beyond technical metadata. So for instance, metadata that is already stored within DICOM files natively or within different proprietary formats. And the metadata should also include domain-specific, domain-relevant metadata about, for instance, the pre-analytical conditions or pathological concepts. So that led to the establishment of the Big Picture metadata standard, which is an umbrella for substandards called CMMS, MSMDAT, MetaFlex, and the dataset file structure standard. I will briefly go through the definition of each of those different substandards, and we will also dive a little bit into each of the different substandards with more depth. However, a disclaimer here at this point already, we will not cover all the substandards very explicitly, but we have a dedicated documentation for that. I will talk about that in a minute. So the CMMS, which stands for Common Mandatory Metadata Structure, defines all the metadata bearing objects that can be found in a dataset or on the repository. And it is based on the EGA metadata model, however, was extended and adapted in order to fit the needs of a repository for digital pathological slides. Beyond the mere structure of the entities, it also defines relations and certain constraints for the creation of datasets. The MSMDAT stands for Mandatory Submission Metadata and defines the minimum information that must be provided for each of the entities defined in the CMMS that have to be present in order to submit a valid dataset to the repository. Metadata is exchanged with the repository or downloaded from the repository and stored by the means of XML files. And therefore, the metaflex defines dedicated XSD schema, so the structure of those XML files that contain the metadata. And it is based on the structure of EGA and has been extended. And it is currently maintained and hosted on the Bigpicture GitHub repository. And my colleague Eric Gabrielson will talk about this specific substandard in more depth later on. And lastly, we exchange data sets with the repository or we download the data sets from the repository by the means of a folder concept. So we submit folders and we can download folders. And in order to facilitate that there is a consistent standard also for the structure of the folders, we have created the dataset file structures standard. And this specifies where the dedicated data artifacts, so the hostlet images or annotation files, as well as the metadata bearing files in the form of XMLs should be stored. So as I already stated before, the metadata standard will only be touched on the conceptual level, and we will provide certain key concepts in order to interact with it. We, on the other hand, have created a very detailed technical documentation already, in which each of the concepts that we talk about today and also the technical specification of each of the substandards is delineated very explicitly. And for project members, the documentation can be found on our SharePoint. And for members who are for attending persons who are not project members who are interested, they can get in contact with us in order to get more information about the documentation. So the CMMS extends the EGA model, and we have here in yellow on top certain entities that we inherited from the EGA model. However, we introduced new entities, and currently the CMMS comprises 15 entities, their relation as well as their structure. And it also specifies certain constraints on datasets, how datasets have to be formed in order to be a well-formed Bigpicture dataset. So we introduced initially an image entity, which relates to a whole slide image, and then also a hierarchical structure of different entities, the slide, which relates to a physical glass slide, a block, which relates to a tissue block that is, for instance, stored in a biobank, a specimen, which relates to, for instance, an organ that has been extracted from a patient, a biological being, which relates to either a patient or an animal. And then we also have a case entity, which can be used in order to group different specimens together. For instance, if certain different organs have been extracted from a patient at one given point in time. We also included a dedicated staining entity that can be used to specify information about a staining procedure that has been performed, an annotation entity, which is thought of conceptually as an encapsulation of the annotation files, which specify interesting subregions of an image, And then most importantly, also the observation entity, which encapsulates pathological or domain relevant information like diagnosis and so forth. The observation entity can then also reference dedicated observers in order to explicitly delineate the observer that performs the observation, and this can be either a machine or a human. At this point, it's very important to make a clear distinction between the metadata entities, so the entities contained in the CMMS, and data artifacts, such as host-led images or annotation files. So they are not equivalent. The entities we talk about in the CMMS are merely the metadata-bearing entities, and they will be stored eventually or serialized to XML files. And then we have the data artifacts, and we have a relation or a reference between those metadata entities and their data artifacts. But CMMS entities can be related to each other. So for instance, we would have an annotation that relates to an image, and annotation itself references an annotation file, and the image itself also references a hosted image, and thereby we also keep track of the relations between the data artifacts. All CMMS entities have a certain base structure, which comprises of identifiers that allow the unique identification of a given instance within Bigpicture. They have references that delineate the relation between entities if the standards defines them. And they also have a container called attributes, and this container stores all the metadata attributes about a given instance, and it contains at least the minimal information defined in the MSMDAT. Note has to be taken that this base structure is extended for certain entities, most notably the observation and the staining entity. In order to store metadata, one has to use CMMS attributes, and attributes within our metadata schema generally follow the tag value paradigm. So you have a name for a given attribute and then a value. However, we have defined certain different types of attributes in order to store different kind of information. The most easiest type is the string attribute, where you just provide a tag, for instance, her2, and then provide a string value like double plus. However, we also have the possibility to encode numeric attributes. Here, for instance, the PDL1 tumor proportion score as a percentage. So the numeric attributes can be stored either as decimals, integers, or floating point numbers. We also have the possibility to encode measurements. Here, one can specify a specific unit together with the attribute. Then for more complex attributes, we have introduced a code attribute type, which allows to code or include coded attributes by the means of providing the code number, the meaning, the scheme version, and the scheme. So for instance, here one could encode the diagnosis with SNOMED-CT and provide the SNOMED-CT code, the term primary non-small cell lung cancer, and then potentially also the version of SNOMED-CT. In order to give even more flexibility, we introduced also a set attribute type, which allows to group together all the aforementioned attribute types and also the set attributes. So one can create also nested sets. And this, for instance, can be used to encode a diagnosis with different other attributes. And we have a certain derivative of this set attribute, which is called code attributes, which should only be used for stating code attributes in the set, and a custom attributes type where one can just provide attributes to the own liking. The important note here is that the code attributes type should only use internationally recognized coding schemas. Now coming to two of the extended entities that go beyond the base structure. The most important is the observation, and the observation is defined as a pathological statement about one of the following CMMS entities. So we allow that one can not only specify observations on an image level, but also on a biological being, a case, a specimen, a block, a slide, an image, or an annotation. And ideally, people should really use the hierarchical level or the real life object that the diagnosis was made about when stating the observation. So if, for instance, it was recorded on a case level in the limb system, one really should use the case entity to relate an observation to. And the observation extends the base structure by a statement element. And this statement element then really captures the actual pathological information and is structured in a 5-dimensional way. We have a type, a status, then these code attributes where the coded attributes live, a custom attributes element where custom attributes can be defined, and a free text. So it basically tries to emulate a structured report. In regards to the type of a statement, which can be used for conceptualization, we have defined diagnosis and finding. Finding here is relevant for the non-clinical partners, and microscopic and macroscopic description. It is of note at this point that one observation only can contain one statement. So if one wants to encode a diagnosis, a microscopic description, or a macroscopic description, 3 different observations with one statement of the dedicated types have to be created. And then we also introduced the status concept because, for instance, one could have a diagnosis of an infiltrating adenocarcinoma of the colon, which was stated on a case level. However, the case is related to many images, and it's not necessarily true that one can find this infiltrating colon carcinoma in all images. And therefore, we have the status summary that indicates that the observation is only true on the level it was stated. And in distinction to that, the distinct status, which assures that the observation or the statement is necessarily true also for all the downstream entities, which potentially is very important for computational scientists or AI scientists that want to really be sure that the stated pathological information is true for all the images they work with. The staining entity extends the base structure with a procedure information element and the possibility to define dedicated stains. Here it's important that procedure information and stains are mutually exclusive. So one either can specify a procedure information or can list dedicated stains. And the procedure information can only be used with chemical stains. So for instance, one can directly encode hematoxylin and eosin as one procedure information, or one can um, store this procedure as hematoxylin and eosin using 2 different stains. For targeted stains, so immunohistochemistry or in situ hybridization, only the listing of the stains is required. The given stains then have also the possibility to state attributes about them, which we will hear a little bit more about in the MSMDAT part of this talk. Besides the structure, the relation of the CMMS entities, we also have a set of constraints that have to be fulfilled in order to create a well-formed big picture data set. And there are 2 constraints that I want to emphasize here. The first one is that for original data sets, so data sets that don't relate to other data sets in the repository, it is important that all references between CMMS entities must reference entities that are actually contained in the data set. And the next constraint that I want to mention is that every image that can be found in a data set has or must be related to a observation of the status type, diagnosis, or finding. And this assures that we really have for every image in the dataset an pathological diagnosis. It must not necessarily be related directly to an image. It can be related, for instance, to a case. However, there must be at least one diagnosis or finding present for every image inside the dataset, or at least it has to be related to it. Coming to the MSMDAT, which defines the minimal information that must be provided in order to submit a dataset. This comprises of a core set of attributes that is mandatory for all submitters. But due to the complexity of the field, we also have defined different contexts and have context-specific MSMDAT attributes that then only have to be provided for members sharing the same context. And at the current state, we only have a clinical and a non-clinical concept. Furthermore, we have grouped the attributes within the MSMDAT into conceptual classes in order to make filtering and identification easier. And we, at this stage, have defined a housekeeping class, a technical class, biological class, access, and legal and ethical class. Every attribute within the MSMDAT has a dedicated specification, which states on the one hand side the entity it is related to, the name, and the machine readable name. Here it is important to say that the machine readable name has to be used within the XML files, so the metadata bearing files. And we also provide information about what specific attribute type has to be used, if NA is allowed or not, what dedicated coding schema has to be used, and for instance for DICOM, if we allow NA in our schema, but DICOM requires some value in an DICOM attribute, what dedicated value is entered and can be associated to an NA value in our context. So here we see, for instance, the specification card for the attribute fixation type, and we can see that we here require that it has to be coded using SNOMED-CT, and in certain instances where, for instance, the fixative cannot be found in SNOMED-CT, we do allow that people can specify the term themselves. I now want to present a selected set of attributes that we have defined so far for specific entities. So for the biological being, we require that the sex and the animal species has to be stated, and non-clinical, and the non-clinical context requires also the termination status and the animal strain. For the specimen, besides the relations of the specimen and the identification, we require an extraction method, a specimen type, the fixation type, the age of the biological being at extraction of the specimen, and an anatomical site. And in instances where not one anatomical site can be extracted from the limb system, we also allow that the list of anatomical sites can be associated to a specimen. For a block, we only require the block preparation, which relates to the embedding method of a given block. And then for a slide, we only require the staining information. And for staining information, we have a rather broad set. For chemical stains, we either require the procedure information or the listing of all the compounds that were used. And for targeted stains, we require that the target has to be stated, the method has to be stated, the type of the reporter, if it is, for instance, fluorogenic or chromogenic, the color of the individual targets, and then also the antibody information like a commercial name or the antibody vendor. Coming now to the conclusion of my part, after defining the general structure, defining the mandatory informations that have to be present, however, can be extended to the liking of a given dataset submitter, we have now also defined the structure of a dataset. And as you can see, a big picture dataset will look like this. So we have a root folder with the name of the dataset, a subdirectory called metadata that contains XML files related to the CMMS entities. Some entities will not be shared with a user when he gets access to a dataset. This will be within the private subdirectory and will only be there at submission time point. And then images will be stored in a dedicated image subdirectory in the form of DICOM files, and annotations will be stored in a dedicated annotation subdirectory. And at this point, we also already have included the landing page subdirectory, which will be related to a specific landing page entity, which will be part of the structure in the next version. And with that, I would like to conclude my part and hand over to my colleague, Eric Gabrielson. Thank you very much.
Okay, I will just change presentation view.
Thank you very much, Max. So maybe in case there's brief questions for Max right away, we can maybe take them now, or we wait until the very last end.
I received a question in regard to the XML files, if they're on a dataset level. I would wait to answer this question because Eric will present how these XML files are serialized and created. And if the question still is then open, then I hope if that's okay, we'll answer the question.
Okay, so I will continue talking about the Metaflex. So Metaflex is the Bigpicture standard for storing and transmitting metadata. It is designed to cover the entities, relations, and attributes that are available in the CMMS. Importantly, it does not include the MSN DAD specifications. In other words, what attributes are required and how they should be formatted are not included in the Metaflex standard. And the Metaflex is an XML format, and the metadata files as XML files together with the images are what makes up a dataset. Oh, there were bullet points also. Sorry, I forgot. So the Metaflex format allows us to serialize the metadata. So serializing data is to translate data structures into a format that can be stored or transmitted. Typically, the serialized format is both machine and human readable. So when you prepare your metadata, you will likely use tools that have some kind of internal representation of the CMMS. And when you submit the metadata, you will need to serialize the data into files that the receiver then can deserialize and load into their representation of the CMMS in the tool that they use. And Metaflex is an XML format, and XML is built up using elements. So an element must have a tag, and in the tag we can specify what type of element it is, for example, a slide element. And an element must also have an end tag, which we represent by having this slash. Or alternatively, there can also be an empty element where we just end the element with the slash. Into the element, we can also add attributes, and these are name value pairs. For example, we can assign the name attribute to our slide. And the attribute can also have content. So it can either be just a string. We can say that this slide is from block A1, but we can be more precise by adding nested element. So we can, for example, in this element, include an element, say in block, and the name of the block, or that it has an image and the name of the image. And Metaflex is designed to describe the CMMS objects, capturing the type of CMMS objects. So we have the CMMS entities, and relating to that, in the Metaflex, we can define the type of the CMMS object, the identifiers, the references, and attributes. And this is how this can look. So first, we have a element describing the type of the CMMS. So this is, for example, a block object defined in the first element. And then we have the alias, which is then the identifier of this block. And these are then defined as attributes. And we must have an alias for our objects. And this is then assigned by the submitter and should be unique within the submission. We can also have an accession attribute, which is optional and will be assigned by the repository. And this accession number should be unique within the repository. We can also add references. So for example, here we have that this block is sampled from a specimen. And the different references we have, they are defined in the standard. So for example, for blocks, we can say sampled from is a reference for what specimen it is sampled from. And again, we are using aliases that are required. So we need to reference the specimen with alias, but we can also add on an optional accession number if we have one. And last, we have the attributes. So the attributes is a collection of elements, attribute elements that the block has. Everyone can see the presentation now?
Yes,
I also have a very long lag of, okay. So this just contains all the attributes that the object has. And In the CMS, we have a lot of different type of object attributes, and they have corresponding metaflex types. So the type of the attribute is stated in the tag of the element. So for example, we can have a numeric attribute stated like this. And this is required to have and should be machine readable and is from the MSN data. Next, we have a value. And this is also something that is required to have and is then depending on what kind of attribute it is, it will look differently. We can also have values that are not known or should not be present, and then we need to specify that it is not known by setting that it is nilled. So the simplest attribute is the string attribute that we use for string values, enumeration, booleans, and datetimes. For example, the sex attribute for a biological being, which we have enumeration F for female. Another attribute is numeric attribute, where we can have either integers or floats. For example, for color depth, which you say that it's 8 bits of color depth. The measurement attributes adds on to the numeric attributes that we also have a unit. For example, a half of a micrometer. And the code attributes we use for having code values. So for example, animal species, we can define with a code, and then the value is subdivided into several more elements. So we have the code, the scheme, the meaning, and the scheme version of the code. And last, we have the set attribute, which then is a collection of attributes that belong together. For example, we have set attributes for scanner attributes, which includes the scanner manufacturer's name and model names and so on. And importantly is that also set attribute has its own tag. So we have a tag scanner for all the elements that are grouped together. So for example, an example of an object we can have is a slide. So we can see that this is a slide object because it starts with the tag slide. And then we have the alias of the slide, which is required, and we call it slide or something, something, something. This slide does not have any special attributes, so it has an attributes element which is nilled. And then it has a reference, it says it created from, and the alias of the block that it was created from. And then it has staining information, a reference for staining information, which also has an alias to the staining procedure that is representing the staining that was done on the slide. And as Max talked about earlier, we can have different type of stainings defined. So one is a staining procedure. A staining procedure would look like this. It has an element with the tag staining, and then defining the alias of the staining procedure. And then comes an element with procedure information, where we state that this is a chemical method, chemical staining, and then a staining procedure defining the procedure used by a code. The other option is to have a staining list, and this that's similar to the previous version. It also starts with the staining tag element, and then the alias for the staining list. But then instead of having this staining procedure, we have one or multiple stains. So we can have one stain here saying this is a chemical stain and the staining compound used, and then we can define several others like this after that. Another object that Max talked about a little bit more was the observation type, and that is quite complex. So we see that it's an observation by the observation tag, and as all of other objects, it also has an identifier here on the alias observation. And the item that this observation is observed on is stated in the observed on element. And in this case, it's the case and the reference to the case. And then we have the statement that is included inside this observation. And as Max said, we have statement type. This defines what kind of statement it is. It can be a diagnosis or finding and so on. The statement status, which is then if it's how this statement applies to the reference the item. And then code attributes, which can be, for example, the diagnosis code. Custom attributes, in this case, the custom attribute contains the diagnosis in the original language. And then free text, which in this case is empty. And the metadata files that we produce, the metadata objects we produce, we arrange them into files based on type. So there will be one XML file that contains all the datasets. Typically, there will only be one image XML file that contains all our image objects, one observation file, one sample file that contains all the samples, and one staining file that contains all the stainings, and so on. And as Max said, we then arrange all these into a folder structure, which is defined in the dataset. Remind me, Max, what it's called? Dataset file structure standard. Yeah, it is on the slide.
Indeed, yes.
And then this metadata Metaflex format is defined in the Metaflex schema files. So these are XML schema definition, or XSDs. And here the animation was completely wrong. So these files defines the valid structure of Bigpicture metadata files and can be used to validate that metadata files you have in XML format are valid. However, these schema files, they only validate the XML structure and not the CMS relations that are defined in the actual metadata, or that the metadata that is in the files have the correct MSN attributes. And the schema files are available on the EMI Bigpicture GitHub. So for working with metadata, we have a couple of different tools. First, we have the Bigpicture metadata interface, which is a Python library for creating, serializing, and uploading datasets. And that is also available in the EMI Bigpicture GitHub. As of now, it's only available for members of the Bigpicture consortium, but it will be later available publicly. Another tool is SlideTap, which is a web app for with a graphical user interface for curating pathology datasets. And that is also available on the EMI Bigpicture repository. So the Bigpicture metadata interface, it represents the Bigpicture metadata model as Python classes, and it contains methods for converting to and from XML. It also methods for validating both the XML structure and that the metadata in the XMLs, of course, are valid based on the CMS requirement and the MSN requirements, and that the image files that are stated in the metadata are present. It can also encrypt and upload metadata and datasets. So an example on how the model is defined in the Bigpicture metadata interface can look like this. So we have, for example, for the block, we can see that we can specify the block preparation, which is an MSN attribute of a block, and we can define what slides are created from this block. And we can use this to build a complete metadata dataset. And when we have done created our biological being and datasets containing images and so on, it's quite easy to just use the interface to convert these into XML. And once we have converted it into XML, we can validate that the XML files are correct. And we can import back from the XML files into the Python model, or we can submit them and encrypt them to the repository. And last, I want to talk a little bit about SlideTap, because SlideTap is a tool that can be used to create, visualize, and curate metadata and image for data set creation. And it has it can export the created data into the Bigpicture metadata format. So in this short demo, the sample hierarchy for a small Bigpicture dataset is presented, going from slide to a biological being. So we can go into a slide and look at the staining procedure. We can go to the block it was created from, the specimen, and a case that is included in, and the biological being that it is being created from. And that was my last slide. So thank you for your attention. And me and Max have been working on this, but it would not be possible to without the help from all other active members of the task force, the metadata task force. So we thank them a lot for their dedication and great work, and for all other that have participated in the Bigpicture project.
Thank you very much, Eric, and Max, of course. And I can only echo that it has been quite a bit of work, and well, we're halfway the project, and I think it's a great achievement that we have established this. I think it's of critical importance for the project. So thank you again, and also the other task force members. So I would like to open the floor for questions. Please, if you have a question, raise your hand and we will.
Rick, should we go through the questions that have already been stated in the chat?
Yes, please. Could you do that?
Yeah, sure. So the first question relates to the question if the metadata model is compatible to Fire, HL7, or DICOM. So at the moment, we don't have any adapters to Fire, HL7, or DICOM. This potentially might be in scope of the project, but at the moment, we have not planned it yet. Maybe Eric can allude to that a little bit in terms of DICOM metadata. We have decided that we will not store or duplicate the metadata that we store in our entities in the XML files into the DICOM files. However, potentially, and here Eric has to assist me, there is tooling to inject the data using the interface into the DICOM files if needed or wanted.
Yeah, what we said is that it's not required to have the metadata also in the DICOM files. There are tools being developed to do so, but also we cannot really represent everything that is in the metadata standard into DICOM. At least I haven't found that to be possible.
Can I add a follow-up question to that? It's more like how would I receive the data set then? As exactly how you showed me with all the XMLs, and I as a user have to then use this metadata how I want to.
Yes, exactly. So you would receive, so that was one of the design choices that we have, that the data set that you receive looks almost the same, besides certain types of metadata that will not be shared as the submission of the data set. It will not be, oh, sorry, I muted myself. It will not be changed by the repository, so you can be confident that the data that you receive is the data that was submitted to the repository. It is outlined in the form which is defined by the data file structure standard. And for instance, you could use the Python interface in order to load in the metadata and create Python classes. At this stage, we have already thought about maybe building some adapters for Python, maybe for making things more easy to interact with. You could also use, for instance, SlideTab in order to load it into SlideTab on your side in order to look at the metadata. However, the metadata will also be present within Cytomine. Maybe Joel Hedlund can elaborate on that a little bit. So we also provide different access modalities to the data.
So just to comment briefly, I'm not a Cytomine developer, but what Max talks about is on the Cytomine roadmap. Cytomine is intended to be the user interface and the way to interact with platform data if you are not a programmer, if you don't like XML files. So on the platform, the datasets will appear to Cytomine just as it appears to people who download the datasets. So Cytomine does have the ability now to parse Bigpicture standard conformant datasets and should be able to display them to you. What is not developed yet is support for life science login, so that you can use your own home institution login to get access to your own platform private Cytomine server. Also support for object storage is not implemented in Cytomine yet. That's on the roadmap for September as far as I'm aware. what's on the roadmap between there is support for storage, so that you can point SiteDomain to a folder that's full of data sets in Bigpicture standard format, and then SiteDomain will slurp them up. And then you will be able to use functionality inside SiteDomain to do queries, for instance, to see only images that have a certain stain or a certain diagnosis or similar.
Thank you very much, Joel. So the question, which was a follow-up question to the Fire and HL7 question regarding OMOP CDM CDISC. So CDISC is used by non-clinical, and as far as I know, the non-clinical partners have already created tooling that converts CDISC datasets into datasets that comply to the Bigpicture standard. Here I would ask that people reach out to Katrina Lyons, right? Rick, correct me?
Lines.
Yes, Lines, sorry. So she's here, great, so I can hand over to her for that. And Open EHR is also current. So for OMOP, CDM and Open EHR, it's the same as for Fire, HL7 or DICOM. We have not created tooling that can interact with those standards, but for CDISC, I would like to hand over to Katrina.
Yeah, so the non-clinical data is handled by Deciphex, and we've created the data transporter. So that is compatible with CDISC send, and it automates all the backend. So it pulls from the send files and maps to the MSM DAG part to upload. So that's automatically handled.
Thank you, Katrina. And then we have one question, maybe if I can ask Dan to just spell it out, then I don't have to read it.
The question more here is like maybe a little bit from like very coarse grain to very fine grained metadata. How strict is it? Like, are some fields only require H&E in a certain way of spelling? Like you have a few choices, and what fields are very open in like free text? A little bit based on the levels.
Yeah. So generally, we have tried to be as standardized as possible. So for the majority of, so maybe to step back a little bit, we have defined the MSM DAT, which specifies specifically all the required attributes, their names, and their specification. And within the MSM DAT, we tried for most of the attributes to use coding schemas. So for instance, for staining, for a chemical compound, we require that SNOMED-CT should be used if one can, for instance, encode hematoxylin and eosin. So that's possible with SNOMED-CT. However, there might be, so we have done some investigation, there might be some very exotic stains that are not found within SNOMED-CT, and therefore we leave it open that one can then specify a string. However, we hope that in future we potentially can also make this into a controlled list or maybe interact with SNOMED-CT in this regard. And for other things, we also do the same. So for instance, for the extraction method and so on. So we heavily try to use SNOMED-CT in order to encode attributes. However, since we also wanted to respect that small groups can create that potentially don't have technical assistance, or we have large institutions that have LIMS systems in which certain attributes are just not captured retrospectively. We do also allow for a certain set of attributes that they can be NA, so empty. So then they have to be present. However, as Eric delineated, they can be nilled. If you are interested more into which attributes, you can definitely contact me. And we're also planning on publishing the documentation, and there it will be clearly delineated which attributes we have so far defined and what is the specification. But generally, we try to be as standardized as possible by being liberal to make it feasible for people to extract the information.
Well said,
I hope that
Mats.
answered the question then.
Yeah. And then the last question is, which is tied to that, is like, do you have some score? Like, how can you score or evaluate the quality of the metadata of a big set. Like if you have million of entries, you're not going to browse manually through them. So how can you check if the quality is high?
So this falls into the realm, I have to say, of the quality control task force. So I can only give a little bit of insight here because I'm not so actively here involved. But the idea is that, so for instance, at our side, we perform tests. So we extract the metadata from our LIMS system, and then we perform tests of 100 cases or 1,000 cases. Currently, we are at the 100 cases where we manually go through the metadata and see if the extraction process was valid, and then get some heuristics. But the quality control task force currently works on recommendations or solutions in order to measure or assure the quality. But if you want to have more information about that, I can refer you to David Brettel, or who is one of the key leaders in the quality control task force.
Yeah, thank you very much.
And then we have another question from Damak Salma. I'd be interested in that list of flexible or nullable attributes as well. Okay, yeah, so please just reach out to me, and I'm sure we can arrange something in that regard.
Okay. I don't know if there's any further questions by anyone. Otherwise, I think we can close the meeting. But first, I would like to thank Max and Eric for their efforts on the metadata and establishing this metadata standard. I think it has been a lot of work, and I think it's very detailed, but I think it's essential for a repository like Bigpicture. Can
I ask one more question?
Sure.
Because maybe it's also not part of this work package, but how about like versioning metadata? How is that done in this schema?
Yes, so so we are also responsible for that. I didn't have a dedicated slide on that, but generally we have one version for the entire standard, and each substandard has its own version. However, once we have a new version of a substandard, also the version of the entire standard changes. And we adopt a semantic versioning process. So with one, if we have, so like in conventional other schemas, when we change the first number, then we have a major break. The second number is when we have some minor changes, and the last one is just some bug fixes. And what we do is in the task force, we first create a draft that is presented. We work on the draft, then we review the draft and accept it as a candidate. And then once a candidate has been accepted, we aim that we actually can get data that complies to the standard. We see if we have problems with, for instance, the tooling or during extraction process, and integrate in the feedback loop this information into the candidate. And once we have integrated or made decision on the feedback, and we have received data that complies to the standard, then the standard gets accepted as an accepted version, and the version number is updated.
And what about versioning the metadata itself? Because I can imagine that this also gets updated.
Yes, so within the data set, there is an attribute that delineates the version of the standard that the data set complies to. It's at the moment on the dataset level. So not every attribute states the dedicated version, but you have a specification of the entire dataset to which metadata version it relates to, and then all the attributes, the entire structure and everything within the dataset have to comply to this specific standard version.
There's 2 comments, I think, or 2 hands. Maybe Joel, we have only a few minutes left, so.
So I don't know if this still is accurate, but the intent for a while was to tie the versioning number of the standard to the amount of effort required on the part of the contributor to make sure your data set conforms to the new version. So if it can be done, the upgrade can be done automatically by the repository. That's probably just a bug fix thing. If it's minor effort, then it's probably a minor. If it requires a lot of attention from a medical professional to make judgments and do an overhaul, well, that's a major revision. Then we've discussed also, it's of course desirable that we have the latest version of all data sets. That makes it easier to do AI across data sets and things like that. So work package 3 will have to, or rather node coordinators will have to decide what versions metadata do we accept presently. Do we accept 2 old versions or just 1 old version, or do we just accept the most recent version? And the repository, of course, validates all the submissions to ensure that they comply to whatever the node coordinators decide that they should comply to. Also, for data sets that are on the platform, a lot of people will want access to old versions of data sets because they were used in AI training or in scientific papers. So you will want that referability to old what was actually used in your research. So we will support that, and that support will be in the form of contributors uploading discrete data sets, new versions of the data sets with different version metadata in them, and we do deduplication so it doesn't cost a lot of extra storage. But if there is a right to be forgotten request, for example, then that data set must disappear. So the data sets will always contain precisely what the contributors asked for. I disagree with Rick's comment that this has not been on our roadmap so far. It has absolutely been on our roadmap. That was part of the initial description that the metadata task force started out with, but if it has been lost during the way, I cannot answer to that.
Maybe I was too fast, Joe. I think it has not been considered so far. It has not been on top of the list, but maybe Max and Eric can comment.
So I would have to ask the concrete thing, what was intended with the question of not being on the roadmap, and then I hope I can give an answer.
So maybe we can do it very quick because it's also 4 o'clock.
Maybe what I can say generally, what Joel has said is within the knowledge of the task force and within the scope, at least as far as I understood it.
Okay. All right, let's close off. Not before telling you that we plan to have another webinar on the 26th of April, mainly focusing on the resource entitlement management system that we will use so for a user to get access to the data. And as Eric already mentioned, there's a tooling available called SlideTab for clinical contributors to convert their data into let's say Bigpicture data, and that is scheduled for late May, similar time on the 24th of May. But of course, you will receive an email about this. With that, I would like to thank all of you for your attention and participation. The recordings of the meetings will be made available, so you can also share it with your colleagues if you want to. And please do not hesitate to reach out to us or to Max or Eric if you want to know more. All right, with that, I wish you all a happy weekend.
Thank you.
Bye-bye.
Bye.
Likewise. See ya.
Thanks all. Bye-bye.